Hello everyone, my name is Kamal and I welcome you all to my YouTube channel and I request all of you please comment, like, share and subscribe to my channel. Today I will discuss two important topics, Latimer diagram and frost diagram. So these are related to electrochemistry and the redox chemistry. So I'll discuss about the how to draw Latimer diagram, how to draw frost diagram and what are the benefits of this and what is the information we can get from this to diagram. Okay, so without doing any further delay, let's start the our uh, discussion. So the first I will discuss about Latimer diagram. Okay, so before introducing the Latimer diagram, I just have to introduce about the redox chemistry. So in chemistry, there is a large, there are large class of molecules or the large class of reactions where which you can classify as a redox reaction or oxidation reduction reaction. Now here I just want to explain what is a redox reaction. So for that I have chosen one of the most important and a very old reaction and famous reaction. This is your Daniel reaction. So copper, zinc copper. So you can see this involved in Daniel reaction. So what is happening? This is an example of redox reaction. So what is happening? So zinc is releasing two electrons, and this is copper is taking those electrons, and finally copper was in 2 plus oxidation state. It is changing to copper plus, and zinc initially it is in 0 oxidation state, and finally it is in zinc 2 plus. So redox reaction is nothing but reaction where you have a transfer of electrons. Okay, an important thing in redox reaction is that oxidation and reduction occur simultaneously. So you cannot have only oxidation or only reduction. So both has to occur simultaneously, and each one which the way I have connected here zinc to zinc 2 plus and copper to 2 plus. Each of them is known as couple. These are known as redox couple. Okay. Now there are various ways to represent. In earlier days, I mean, if you see the old books, the data were represented in terms of reduction potential, oxidation potential, but now all the data are represented in terms of reduction potential. Reduction potential means whatever be the couple, you have to represent the couple in this form. That means the reduced form should be on the right hand side and the oxidized form should be on the left hand side. Okay. Uh, so in both cases, if you want to write for copper, copper is already in this form, I mean oxidized in the left hand side and the reduced form in the right hand side. But in case of zinc, you need to change it. Okay, zinc 2 plus should be here and zinc should be here. So this is known as oxidized species. This is known as reduced species, and the potential for this reaction is known as reduction potential. Okay, whenever you write a redox couple in this form, the potential it corresponds is known as reduction potential. Okay, now I have described about the redox reaction, what is a redox reaction and reduction potential. So this is the convention. Now we are ready for Latimer diagram. So Latimer diagram is a very simple diagram. The definition is like that. Oxidation in this diagram, the oxidation numbers decrease from left to right, and the numerical value of the reduction potential or the redox potential in bold are written above the line joining the species involved in the couple. Okay, so this sentence will be clear with this diagram. So these are known as Latimer diagrams. Okay, now here I have given only two examples, one for chlorine and one for manganese. So this is the Latimer diagram for chlorine at pH 0, and this is the Latimer diagram for chlorine at pH 14 or POH equal to 0. Now how I have represented the highest oxidation state species should be on the left hand side, and then gradually you have to write down the lowest minus 1, and the corresponding redox potential or the corresponding reduction potential I have to write in the arrow joining the two species. Okay, so this is the way you represent your Latimer diagram. So this is for manganese, exactly similar. The lowest is here and the highest is here, and the corresponding reduction potential I have just put on the arrow connecting the two species. So this is for these two species and so on. Okay, so this is the definition of Latimer diagram and also examples of Latimer diagrams. Now let us solve the problem where I have to use the Latimer diagram. Now using the Latimer diagram, calculate the value of reduction potential for this couple ClO minus Cl2 in the basic aqueous solution. So it is very important since they are asking in the basic aqueous solution, and I know that there are two Latimer diagrams possible for chlorine. So I have to choose the correct one, and this is the correct one at pH 14 in the basic condition. Now the question they're asking is that I need to determine the redox potential for this reaction, but there is no direct way. I cannot write down the reduction potential for this reaction and reduction potential of this reaction to get the reduction potential of this reaction. Okay, so that is not possible. Now, how to do that? Now, in order to do that, I will use thermodynamics and something called Hess's law. So here, this reaction I have written here. So ClO2 minus and 2 electron, because from plus 2 to plus 1 you'll get this one, and this one again will take 1 electron. Finally it will produce chlorine. Okay, now for this reaction I can write down the delta G value. For this reaction also I can write down the delta G value. Now because Gibbs free energy is a state function, so I can add them. Now you see this final reaction. If I add these two reactions, I will get ClO2 minus plus 3 electron and half, which is exactly what I want, because I want the redox couple for redox potential for this reaction, and this is this reaction. Now the point what I'm making, by adding this two reactions and I can get this reaction, that means if I add the Gibbs free energy of these two reactions, I can also get the Gibbs free energy of this reaction. Okay, now if you know the Gibbs free energy, you have a formula which connects the potential, okay, related by N. N is your number of electrons involved in the reaction, and this F is your famous Faraday constant, and E is our reduction potential. Now if you use this formula, you will end up with this kind of equation. Okay, let me explain this equation. Now I want the reduction potential for this reaction. Okay, ClO2 minus to chlorine. Now in order to determine the potential, what I have to do, I need to look the Latimer diagram and see any intermediate steps are there or not. Okay. So Latimer diagram says that yes, there is one species involved. Okay, I cannot go directly. Now it's very easy. What to do? First you see this step. Okay, how many electrons are involved? 2 electrons involved. So what is the potential? 0.63. Once it is done, next from here to here, how many electrons are involved? 1 electron. What is the potential? 0.42. And for the total, for the main reaction, how many electrons are involved? 3 electrons are involved. So just do the calculation with the calculator and you'll get 0.59 volts. So from the Latimer diagram, I can calculate the redox potential of any couple. And in order to do that, I need to use this formula which I got from this equation, and I need to know how many different species are involved while reaching to the final step. Okay, since here there is only one step, so first step, second step. In the first step, 2 electrons, potential 6.68, and in the second step, only 1 electron, potential 0.42, and the total number of electrons involved is 3. and you can just calculate it. So this is the one of the important application of Latimer diagram. Okay, let's move on to another important application. This is known as disproportionation. That means what? A species has a tendency to disproportionate into its two neighbors if the potential on the right hand side of the species in a Latimer diagram is higher than that on the left. So here I have taken a small fragment of the Latimer diagram for manganese. So manganese 3 plus, I'm asking a question that is there any chance for this manganese 3 plus to form manganese 2 plus and manganese 4 plus? So this reaction is known as disproportionation reaction. Okay. Now this sentence is saying that this definition is saying that if the potential on the right hand side, so there are two neighbors, if the potential on the right hand side is greater than the potential on the left hand side, then this species will undergo your disproportionation, otherwise not. Okay, so if you see the value is 1.56 is larger than 0.90, that means this manganese 3 plus will go disproportionation, will undergo disproportionation. Okay, so this is one of the important application of Latimer diagram. So it is saying that just by knowing the just by looking at the diagram, you can tell that a particular species is stable or not. The meaning is that this molecule or this species will not be stable and it will convert to Mn2 plus and Mn4 plus. Okay, so this is the disproportionation which I got from Latimer diagram. Okay, by just looking at the diagram, if it is higher, it will go disproportionation. If it is not, it will not go disproportionation. Okay, now let's discuss about the frost diagram, and this is also very important, and this gives this is little easier to interpret, although you need to do a little bit more work to get the diagram. Okay, the definition is like this. The frost diagram shows how the gives energy of formation of different oxidation state of an element vary with the oxidation number, and the most stable oxidation state of an element corresponds to the species that lies lowest in its frost diagram. Okay, so here I just want to explain this concept of frost diagram. It's a simple example where I have chosen oxygen as my element, which is changing the oxidation state. So here it is 0, -1, minus. Okay. Now, by definition, Gibbs energy is nothing but Ne. Okay, so already discussed this equation. Now, the most important point while plotting the frost diagram is that I need to write down first. Basically I need to write many equations based on the number of species I have, and while writing the equation, in the right hand side I have to write the species which have the zero oxidation state, or normally we can call in its elemental form. Okay, the element oxygen elemental form is your oxygen gas. Okay, or in simple sentence you can say you need to write down the species which have zero oxidation state on the right hand side, and other species. For example, there are two species are there, H2O2 in H2O on the left hand side, and the electron you need to write down to adjust the oxidation state. Fine. Now there are two species. Let us first consider H2O2. H2O2, the oxidation state here is -1. Here it is 0. That means it has to release one electron, so it is negative. Similarly, here also I put the oxygen, okay, because it is the elemental form or zero oxidation state. And the next one is the water. Here it is -2, so 2 electron it has to release. And this is the reduction potential for this couple. Okay, oxygen water couple, oxygen peroxide couple. So this is the reduction potential for oxygen peroxide couple, and this is the reduction potential for oxygen water couple. Now, how to determine Ne? So N is given here -1. E is 0.70, so I'll get a minus 7, sorry, 0.70, and there are N is minus 2, so I'll get, if you multiply with 1.23, you'll get minus 2.46. Okay. Now, once this is done, what you have to do, you need to plot the graph where in the x-axis you have the oxidation state, and in another case you need to write down this. In y-axis you have the Ne values. Okay, these are involved. X-axis oxidation number, y-axis Ne value. Now you just plot and just you'll see that this is the situation, and so the most stable oxidation state you can determine from the graph is water, because it is lying in the lowest in the your frost diagram. Okay, so one more information I just want to tell you is that this disproportionation you can also explain with the help of frost diagram in a very easy way. Suppose this H2O2 we want to determine will undergo disproportionation or not. Then what you have to do, you have to draw a straight line between the nearest neighbor. Okay, so the nearest neighbor is oxygen this side, and the nearest neighbor in this direction you have water, H2O, and you just draw a straight line. If this species lies above the line, okay, that means this will undergo disproportionation. If it is not, it will not go. So this is the two important information you are getting from the frost diagram. What is the, or which is the most stable oxidation state, or which is the most stable species? And number two, it's very easy to determine that which species will undergo this disproportionation or not, just by drawing a line between the nearest neighbors. So if the species lies above the line, so here you can say that the peroxide, it is lying above this line, so this species will undergo disproportionation. Okay, so again I will give one more example of manganese, which is very important. Already I described about manganese in Latimer diagram also. Now here lots of things you have to do if you want to plot this diagram. It's not so quickly you can make it. You need to first determine all the reaction like this. Okay, so manganese in the elemental form or zero oxidation state on the right hand side, and in the left hand side you need to write down all the other species. Okay, so you have to start from, for example, Mn 7 plus 6 plus 4 plus 3 plus 4. Okay, and once you get these equations right and the number of electron it involves and the potential it has, finally you just multiply these two numbers, number of electrons involved and the E potential. So remember, this sign is very important, which I have already described in case of oxygen. Now this what I have drawn in origin. So you can see that the lowest one and the is your manganese 2 plus. That means out of all the oxidation states, the manganese 2 plus is the most stable oxidation state. And if you ask the question that manganese 3 plus will be undergoing your disproportionation or not, which already I have explained in the Latimer diagram. Here it is much more easier. You just draw a line connecting the nearest neighbor, and here you can see that this point is lying above the line. Okay, this manganese species is above the line. That means this species will undergo disproportionation. So that is a key point you need to remember. So this is very important to know the stability of the different oxidation states, and frost diagram does it in a moment. Once you know the diagram, you are done with many things you can determine. Now in this video I discussed about the Latimer diagram, and I'll discuss about the frost diagram, and also determine how to calculate the couple which are not reduction potential of the couple which are not directly connected. Okay, which already I have explained in the Latimer diagram. For example, if I want to calculate the redox potential between 7 plus and manganese, so you need to just follow what I explained earlier. So thank you all of you for listening to my video, and please once again I will request all of you to please like, share, subscribe, and comment. So if you guys have any doubts regarding this, please comment. I'll be happy to answer them. And if you found any mistakes, please point out so that I can rectify it. Thank you all. Bye bye for now.